All right. Hi, everyone. Welcome back to class. For today's guided notes, we're going to work through this worksheet together. You should have the exact same one in front of you. And so we're going to go ahead and try to fill in these blanks as we go. Don't try to copy everything down first and catch up later. The purpose of having things this way is so that you can try to remember what's going on. All right, so today we're going to finish up talking about new content when it comes to the gas laws. And today we're talking about Dalton's law of partial pressures and the ideal gas law. So up to now, every gas law we've learned has treated the gas in a container as one single substance, right? So Boyle's law, Charles' law, Gay-Lussac's law, all of them, they all assume that you have only one gas. But what about the air in the room that we're sitting in, or I guess you're sitting in? It's not just one gas, it's a mixture. It's mostly nitrogen, but it has a little oxygen, a little argon, trace amounts of carbon dioxide. So what happens to pressure when you have multiple gases in the same container? Well, Dalton's answer here is that each gas behaves independently. It exerts its own pressure as if the other gases aren't even there. And we call the pressure that a single gas exerts in a mixture its partial pressure. So first, I want us to remember a couple of terms here. The first is pressure. Remember that pressure is defined as the force exerted by a gas as it collides with the walls of the container per unit area. Okay. In this case, the partial pressure is going to be the pressure exerted by a single gas in a mixture as if that gas occupied the container alone. And so what we're doing here is we are adding forces, right? We are adding forces together. So in a mixture, each gas exerts its own pressure independently to the others, and this is due to the intermolecular forces of each gas being dependent on things like the size of the nucleus and the strength or size of their bond, if they have a bond, and the number of electrons. Remember also that more electrons generally induce a stronger London dispersion force. All right, so before we go any further, I want to see if you can go ahead and fill this in on your own. Take a guess. The total pressure of a gas mixture equals blank of the blank pressures of each gas. Okay, so maybe you don't know what we're doing here. Maybe you don't really know what's going on. Turn to your neighbor, see if they have a better idea. Take about 10 seconds. How would they fill this in? All right, it's a little less than 10 seconds, but I got bored. So here we go. The total pressure of a gas mixture is equal to the sum of the partial pressures. The sum of the partial pressures. Sorry for that bad S there. Oh, I don't know what I did. Okay. The sum of the partial pressures. And it follows this equation down here, that the total pressure is equal to the pressure of gas 1 plus the pressure of gas 2, and so on and so on. And so to label what each of these things mean, it's pretty self-explanatory, right? The P total is the total pressure of the gas mixture. Total pressure. Sorry, that's kind of bad handwriting. Of the mixture. Whereas P1, P2, and P3, etc., these are the partial pressures of each individual gas. All right. Great. Before we try this out on our own and we try to do our own problems, there's a couple of things I want to point your attention to two things in particular. The first is units. All the pressures in your equation have to be in the same unit. They have to be in the same unit before you try to add them. And that's really important because, like, you can't add millimeters of Hg to bar, to torr, to pascals, to atmospheres, right? They're all different. And so we just need to put them all in the same unit before adding. Secondly, I want to talk about gas collected over water. This comes up constantly in labs and even on the AP exam if you decide to take that in a few years. When you bubble a gas into a tube of water and collect it, the gas that comes out isn't pure. It's mixed with water vapor, right? So the total pressure ends up, the water vapor ends up exerting its own partial pressure. And so the total pressure you read includes the pressure from the gas and the pressure from the water vapor, right? The total pressure includes the partial pressure from the water. Explicitly, it's going to be the water vapor. And so the way that we have to correct for that is to get the pressure of just the gas, we have to take the total pressure and subtract the pressure of water vapor. So you subtract the water vapor pressure to isolate the gas that you care about. And so in this case, the vapor pressure of water depends only on temperature. Depends only on temperature. And it will always be given to you. I'm not going to have you try to calculate it on your own, so you don't have to worry about that. Great. Shall we try some practice problems? So let's consider this. Before we even get started, because you've all flipped to a new page, let's go ahead and take a second and write the equation at the top. All right. The total pressure is equal to P1 plus P2 plus P3 ... plus Pn. P sub n just means of any number, right? Usually we won't be handling more than a few at a time, but you could technically have an infinite number of gases. So, well, maybe not infinite, but nearly infinite. All right, so let's look at this problem here. A container holds three gases: nitrogen at 0.4 atmospheres, oxygen at 0.25 atmospheres, and argon at 0.15 atmospheres. What is the total pressure inside the container? Well, that should be pretty self-explanatory, right? Well, all we're going to do is we're going to say the total P is equal to P1 plus P2 plus P3, etc. So we've got 0.40 atmospheres plus 0.25 atmospheres plus 0.15 atmospheres. Great. And we go ahead and we grab our handy dandy calculator, and we have 0.40 plus 0.25 plus 0.15. And we end up with a total P of 0.80 atmospheres. That's it. Easy peasy. Let's look at the next one. A gas mixture has a total pressure of 1.80 atmospheres. It contains helium and neon. And so what's the partial pressure of the third gas, carbon dioxide? Again, should be fairly straightforward. We just look up at the top at our handy equation, and we would say, okay, well, we've got 1.80 atmospheres is equal to 0.60 atmospheres plus 0.75 atmospheres plus P of CO2. Great. And then we can just grab our calculator and do 1.80 minus 0.60 minus 0.75, and we get 0.45 atmospheres is equal to the pressure of CO2. Great, following along so far? Pretty easy? Nice. Let's go ahead and look at this next one. A student collects hydrogen gas over water at 25 degrees Celsius. The total pressure in the collection tube is 742 millimeters of mercury. The vapor pressure of the water at 25 degrees Celsius is 23.8 millimeters of mercury. What is the partial pressure of the dry hydrogen gas? Remember that if you collect something over water, the vapor is mixed in with the gas. And so we have to subtract the water vapor pressure to find the pressure of the gas alone. And so in this case, the total minus the total pressure minus the pressure of the water is going to give us the pressure of the hydrogen gas by itself. All right, so we've got 742 millimeters of mercury for our total. We have 23.8 millimeters of mercury for our water, and that should give us the pressure of our dry hydrogen gas. So we go over to our calculator. And we get, oh, I got a syntax error. All right, 718.2 millimeters of mercury. I did something wrong. Can anyone identify what it is? It's significant figures. So remember, when you're doing addition and subtraction, you can only go to the most precise place value of the least precise number. So you have to look, where do the place values go? Here, this number only goes down to the ones place. Here, this one goes down to the tenths place. That means that if I were to rearrange this, I'd have something like 742 minus 23.8. Anything that's on this side here, when I do that subtraction, is not significant. So I have to round. Great, so my final answer here should be 718 millimeters of mercury is the pressure of my dry hydrogen gas. A little tricky there. All right, gonna have your sub, Dr. Metters, go ahead and pause the video now so that you can practice this on your own. Go ahead and try it. All right, so hopefully you've paused it, you had a chance to go through it, and now I'll go ahead and solve it. So a gas is collected over water at 30 degrees Celsius in a 500 milliliter container. The total pressure is 760 millimeters of Hg, and the vapor pressure of water at 30 degrees Celsius is 31.8 millimeters of Hg. Oh man, I made a mistake because I didn't give you the conversion, did I? No wonder you couldn't solve it. Shoot. Let's see here. I wrote it down in my notes. So the conversion factor here is that 1 atmosphere is equal to 760 millimeters of mercury. All right, so let's do this again. The total pressure is equal to 760 millimeters of mercury. And the pressure of the water vapor is 31.8 millimeters of mercury. So the partial pressure of the dry gas is going to be the pressure total minus the pressure of just the water. And so we got 760 millimeters of mercury minus 31.8 millimeters of mercury. And when we do that, we will get 728.2 millimeters of mercury. Remember that this number here, this last digit, is not significant. So now what we're going to do is we're going to say, all right, we have 728.2 millimeters of mercury, and we're going to convert that. And we're going to say that 1 atmosphere is equal to 760 millimeters of mercury. And so we'll do our answer divided by 760, and we will get 0.958157. Great. This is atmospheres. Okay. Great. Remember, this guy here is not significant. This guy here is actually exact. So this guy here is exact. So this is an infinite number of significant figures. So because this guy is not significant, we only have 3 sig figs here. So we got 1, 2, 3. And our answer is 0.958 atmospheres. All right. Well, sorry about that confusion. Hopefully you're getting the idea here that this is pretty easy, pretty straightforward. And so hopefully you're feeling pretty good about this. Let's go ahead and move on to the next concept here, the ideal gas law. So before we even get started, let's go ahead and talk about an ideal gas. Every gas that we've studied so far has assumed that the gas is ideal. And what that effectively means is that it's a model. It's a model or a hypothetical gas whose particles are assumed to have no volume and no intermolecular forces. That is, no attraction or repulsion between the particles at all. Real gases aren't actually ideal, but under many conditions, they actually come close enough so that the model works super well, and that way we don't have to correct. The correction formula is actually really convoluted, and we don't normally teach it in high school chemistry, and so we can just kind of avoid it by using an ideal gas instead. You're very welcome for making it easy on you. So, a real gas behaves most like an ideal gas when the temperature is very high. That is to say that the particles are moving very, very fast, and so any interactions that there could be are super brief. It also works very, very well when the pressure is very low. That's because the particles are far apart, and so the volume of the particles is negligible in those cases. And so when we're in either or both of these scenarios, you can actually just kind of throw out the correcting factors altogether, the ones that I said earlier that we weren't going to use because we're not. But you might be interested to know that a real gas behaves most like an ideal gas in these two scenarios, which is pretty cool. All right, so let's keep on moving. Unlike the laws that we've studied so far, the ideal gas law works with all 4 gas variables at once, right? So Boyle's law and Avogadro's law and the Gay-Lussac law and Charles' law, they all will, and even the combined gas law, they are all missing at least 1, if not 2 variables, right? The ideal gas law actually puts all 4 of them together. And so if we look at this table here, we can see that we have the four different variables, and they all have specific units that I've put them in. I've also indicated over here on this end what each of these units means, what it measures, right? So in the case of pressure, it's the force per unit area exerted by gas particles. In the case of volume, it's the space that it occupies, right? So these are things that you already know, right? We're going to add in a new constant here, and that's called the gas constant. It's denoted by a capital R. And more or less what it does is it takes all of our different variables that we have, the pressure, volume, temperature, and moles. And what it does is it basically takes our silly human units and allows them to talk to one another, right? Which is why it's a constant, because each of these ways of understanding things, the pressure, volume, temperature, moles, each of those ways of understanding things are man-made concepts. And so all we're doing is adding a single correction factor. You don't really need to know the why around it. You really just need to know what it is, because it's going to be useful, right? And so the units of R actually tell you what units your other variables have to be in order for things to work. And so you really want to memorize this value and its units, because it's going to be really, really helpful for us. So because of this, we know that pressure must be in atmospheres, right? Here it is right here. Pressure must be in atmospheres. Volume must be in liters. Temperature must be in Kelvin. That's not new. Right, we've known that they need to be in Kelvin. And remember that the conversion factor here is Kelvin is equal to the degrees Celsius plus 273.15. Great, and moles must be in moles. That one's easy to remember. I'm having a hard time writing this. Moles. Great. All right. So below here, I have our equation. PV equals nRT. It's often referred to as PIV-NERT. PIV-NERT. I don't know why, but even to this day, I first learned this when I was in 10th grade. That was in 2010. That's 16 years ago. And I still remember this. So that's great. Here's what I want you to do. I want you to pause the video, and I want you to just take a second and rearrange the equation to solve for each variable individually. Solve for P, V, N, and T. Go ahead, pause the video, and try that now. Great. So hopefully you had a chance to do that, and I'll go ahead and do that now. So in this case, P is equal to nRT over V. Solving for V, V is equal to nRT over P. Solving for N, N is equal to PV over RT. And solving for T, T is equal, sorry, I lost myself here. T is equal to PV over NR. Great. I'm going to go ahead and recommend that you just very quickly solve for the variable that you're looking for first before you plug everything in. It's going to make things a lot easier for you down the road. So I'm really going to recommend that you do that. All right, ready for some practice problems? Before we go any further, I am going to do a couple of things for all of these practice problems. I'm going to list all the known variables with their units. I'm going to identify the unknown. I'm going to convert temperature to Kelvin if I need to. I'm going to check that the pressure is in atmospheres and the volume is in liters. I'm going to write out the ideal gas law and then rearrange it for the unknown. before I substitute, and then I'll include my units throughout my work and make sure that they cancel correctly, right? And these are the kinds of things that I want to see you doing as neatly as you can when you're doing assessments, okay? So, to that effect, let's go ahead and start practice problem number 5. A sample of gas occupies 8 liters at 2 atmospheres and 27.0 degrees Celsius. How many moles of gas are present? Okay, so what do we know? We know that the pressure is 2.00 atmospheres. We know that the volume is 8.00 liters. We know that the temperature is equal to 27.0 degrees Celsius. And the number of moles, we don't know. Great. For your reference, what you might want to do at this point is write the ideal gas law up here. PV equals nRT, Pivnert. Also, if you don't remember what the gas constant is, 0.0821, you're going to want to go ahead and do that. R is equal to 0.0821. And remember, that's liter atmospheres per Kelvin moles. Or if you prefer, you could write it this way. That works fine too. All right. So we've listed all of our known variables with their units. We've identified the unknown. Do we need to convert the temperature to Kelvin? Yes, we do. Remember, we have to add 273 to get to Kelvin. So that's going to be 300 Kelvin. Great. Now I can check that pressure is in atmosphere and volume is in liters. Pressure is in atmosphere, good. Volume is in liters, good. And so I can write out my ideal gas law. PV equals nRT. And I'll go ahead and rearrange this for n. N is equal to PV over RT. And now I can go ahead and plug everything in. I'm actually going to do it off to the right a little bit, so I have a little bit more room. N is equal to the pressure of 2.00 atmospheres times 8.00 liters over 0.0821 liter atmospheres per Kelvin moles times the temperature, which is 300. All right. Now we can go ahead and grab our calculator. 2 times 8 divided by 0.0821 divided by 300. All right. So what I got was 0.64961. Atmospheres cancels with atmospheres. Liters cancels with liters. Kelvin cancels with Kelvin. And we're left with 1 over moles, which is the same thing as moles. And so my answer is in moles. Great. If this algebra here confuses you, you should set up a time to come meet with me. Excellent. One more thing that we have to do here. Do you know what it is? We got to do significant figures. Okay, so we have 3 sig figs here, 3 sig figs here. How many here? It's 3 sig figs. And here, I did a bad job of preserving my significant figures there. And so if you come back over here, we know that we have 273 plus 27.0. I could do 27.3, I could do 273.15 if you prefer. Whichever one you did is going to change how many sig figs you need. In this case, if I do the 0.15, I get 0.15, and I actually have 4 significant figures. But if I only did 273, then we lose this extra sig fig. We only have 3 in the end. Either way, it doesn't actually matter if this guy over here, the temperature has 3 or 4 significant figures, because we have 3 here and 3 here and 3 here, which means we need 3 in our answer. And so if this is our last term here, then we round up like this, and we get 0.650 moles of gas. And that's my answer. All right. Not too shabby. Let's keep going, shall we? Okay. Next question. How many liters does 0.500 moles of gas occupy at 1 atmosphere and 0 degrees Celsius? Remember that 0 degrees Celsius is very, very common, right? We've got 1.00 atmospheres and 0 degrees Celsius. That's standard temperature and pressure, okay? We need to make sure that we convert this to Kelvin, okay? We'll get 0 degrees Celsius a lot. We need to convert it to Kelvin. All right, so let's go ahead on the side and write out the variables and see what do we know. We've got 0.500 moles of gas. That's going to be N, 0.500 moles. We've got 1 atmosphere. And we have 0 degrees Celsius, which is going to come out to 273.15 Kelvin. Okay, now the question is asking for liters. We know that liters is volume, and so we know that that's what we're looking for. So we can go ahead and write out PV equals nRT, and we can solve for volume. Volume is equal to nRT over P. And so let's go ahead and plug everything in. Volume is equal to the number of moles, 0.500 moles, times our gas constant, 0.0821 liters times atmospheres per mole Kelvin, times our temperature, which is 273.15 Kelvin, all over 1.00 atmospheres. Great. So we can go ahead and plug that into our calculator. 0.5 times 0.0821 times 273.15 divided by 1, and we get 11.2128. All right, moles is going to cancel with moles. Kelvin is going to cancel with Kelvin. Atmospheres will cancel with atmospheres, and we're left with liters. Great. 3 significant figures here, 3 here. Because of our math over here, this guy is also only going to have 3 sig figs, and this guy is 3 sig figs. 1, 2, 3. My volume is 11.2 liters. Great. All right. Oh, more practice? Yes. Yes, it is. I want you to go ahead and try number 7 on your own or in pairs, depending on the prerogative of your substitute. Go ahead and pause the video and try that now. All right. Hopefully you've had a chance to go ahead and work on that. I just want to write up at the top that R is equal to 0.0821 liter atmospheres per mole Kelvin. Just to remind myself. And of course, if we wanted to, we could write PV equals nRT. All right, so I'll start off by putting my variables off to the side and filling in what I can. A rigid 10-liter container, that's 10.0 liters of volume, holds 2.50 moles of nitrogen gas, and we are at 300 Kelvin. What's the pressure inside the container? All right, well, we have PV equals nRT. I can solve for P, just like that. And I'll go ahead and fill everything in. P is equal to the number of moles we have, 2.50 moles, times our gas constant, 0.0821 liter atmospheres per mole Kelvin, times our temperature, which is 300 Kelvin, over our volume, which is 10.0 liters. And so our pressure then, if we plug that into our calculator, is 61.575 moles, cancels with moles, Kelvin cancels with Kelvin, liters cancels with liters, and we're left with atmospheres. 3 sig figs, 3 sig figs, 3 sig figs, 3 sig figs. We need 3 sig figs in our answer. So my pressure is 61.6 atmospheres. Awesome. All right, let's go ahead and look at question 8. In fact, maybe you'd like to do it on your own. Why don't you go ahead and try it on your own, and then I'll solve it in just a second. Go ahead and pause the video now and try it. Alrighty. Hopefully that wasn't too challenging. Let's go ahead and do what we've been doing, running out along the side, our different variables. And we can say a 5-liter tank contains gas at 152 kilopascals and at 57 degrees Celsius. How many moles of gas are in the tank? All right, we got a couple of things to do first, right? We have to make sure that everything is in the right unit. Remember, if you can't remember what the right units are, let's look all the way up at the top. These are our correct units: liters, atmosphere, moles, and Kelvin. Do I have everything in liters that needs to be in liters? Yes, the volume is in liters. Do I have the pressure in atmospheres? No. Let's go ahead and solve that now. 152 kilopascals. I'll draw my box. I've got my conversion factor up here. Oh, that's not what I wanted. All right. 1 atmosphere is equal to 101.3 kilopascals. I'll grab my calculator. And I'll get 1.5. Let's see, 3 sig figs and 4 sig figs, 1.50. Why does it keep doing that? feel like an old man with my technology. 1.50 atmospheres. Okay. Now we can do temperature. Temperature, remember, we just add 273.15. All right. 57 plus 273.15 gives me 330.15 Kelvin. Great. And of course, we're looking for the number of moles. So I'll go ahead and write out PV equals nRT. And then I can solve for moles. N is equal to PV over RT. Let me go ahead and fill everything in. N is equal to the pressure of 1.50 atmospheres times the volume, 5.00 liters, over our constant, 0.0821 liter atmospheres per mole Kelvin, times our temperature, which is 330.15 Kelvin. All right, let's plug this into our calculator. 1.5 times 5 divided by 0.0821 and 330.15. I got 0.27669.8. Let's see, atmospheres with atmospheres, liters with liters, Kelvin with Kelvin, and we're left with 1 over moles, which is the same thing as moles. Perfect. 3 sig figs here, 3 sig figs here, 3 sig figs here. We actually have 4 here if you follow the math that we did earlier. We've got 4 sig figs here, and so we need 3 in our answer. 1, 2, 3, and so N is equal to 0.277 moles of gas. Perfect. I'm just going to double check that I got that right. Yep. Awesome. All right. Last but not least, why don't you go ahead and try this one on your own? And I will be back with you in just a moment. All right. Let's go ahead and read this. A gas is collected over water at 25 degrees Celsius. The total pressure, I'm actually going to fill this out as I go. The temperature is 25 degrees Celsius. The total pressure is 755 millimeters of mercury. And the vapor pressure of water at 25 degrees Celsius is 23.8 millimeters of mercury. The volume of gas collected is 3.50 liters, and we want to know how many moles of just dry gas is collected. All right, so the first thing that we have to do is we have to get the pressure of the gas all by itself, and that's pretty easy. The pressure of the gas is just the total pressure minus the vapor pressure of water. So let's go ahead and start with that. We were told that the total pressure is 755 millimeters of mercury, and, it's supposed to be a minus sign, and that the vapor pressure of water is 23.8 millimeters of mercury. So the pressure of the gas by itself is 731.2 millimeters of mercury. Remember that this 2 is not technically significant, but we're going to retain it for now because it could make a difference in our overall calculation. So we'll take significant figures at the end, but my pressure of my gas only has 3 sig figs. Now what I need to do is I need to go ahead and fill that out here. The P gas is equal to 731.2 millimeters of mercury. Remember that my R constant gives me the units that everything needs to be in. And we can see here that the pressure is not in the right unit. So the next thing that I'm going to do is I'm going to take the pressure of my gas, 731.2 millimeters of mercury, and we're going to go ahead and convert that. Now for your, you could have either gone all the way back to when I gave you that earlier, or you could just look down here at these conversion factors. 1 atmosphere is 760 millimeters of mercury. And so we've got 0.9621. Now, I'm just going to go ahead and take significant figures now so it doesn't get too confusing. Remember, there's 3 significant figures here, and so we'll have 3 significant figures. And yeah, let's do that. And that's in atmospheres. Perfect. All right, so I'll go ahead and add that over here. 0.962 atmospheres. All right, what were we doing again? A gas is collected over water at 25 degrees Celsius. Okay. So we've got the pressure, we've got the volume. Oh, the next thing we need to do for the temperature, we need to add 273.15 to get our degrees Kelvin. Sorry, I said degrees Kelvin. It's not degrees Kelvin, it's just Kelvin. That's 298.15 Kelvin. All right, I think we have everything we need. We've got things in liters, we've got things in atmospheres, we've got things in Kelvin, and we're looking for moles. So what I'll do is I'll go ahead and write out PV equals nRT, and then I'll solve for moles. N is equal to PV over RT. And I can plug everything in. N is equal to the pressure, which is 0.962 atmospheres, times my volume, which is 3.50 liters, over my gas constant, 0.0821 liter atmospheres per mole Kelvin, times my temperature, which is 298.15 Kelvin. And I can grab my calculator. Just typing away here. All right, and I got I've done something wrong here. What did I do wrong? Well, here's what I got. I'll tell you what I got, and then we'll see if I can figure out what I did wrong. 0.1375. Oh, I know what I did wrong. Haha. This guy right up here. It's not 3.50 liters, it's 0.350 liters. Now, I know that if I were there in person, you guys totally would have picked that out earlier. Okay, that's only going to change my answer here. Let's see. That's just going to put me off by a factor of 10, so that's easy to fix. So that means that this is really 0.0 0.013755. Atmospheres, the atmospheres, liters with liters, Kelvin with Kelvin. We're left with moles. And we'll take significant figures. Of course, there's 3 sig figs, 0.0138 moles. Nice. Wow, that was a pretty complicated problem. But if that's the most complicated kind of problem that you'll see, that's not too bad, right? All right, so this ends our new content. What you're going to do now is you've got a worksheet that's going to combine all of these different kinds of problems together. Boyle's law, Charles' law, Gay-Lussac, Avogadro's law, the combined gas law, Dalton's partial pressures, and the ideal gas law. Wow, that's a lot of stuff to know and work with. Remember to write out your units. Remember to write out which formula you're using. Those things are really essential. If you have any questions, please feel free to set up office hours with me. I'm very happy to meet with you and talk about this. Best of luck. Talk to you soon.